All right, so today we start a brief introduction to lattices in cryptography. This is going to be like basically almost the last topic that we have in the class. But I think it was a good idea to see the codes first, give an introduction to that, then you'll see that lattice-based cryptography is based on a very similar idea. Okay, so usually we talk about the math first, and then we see the crypto, but I think it's nice in this case to just give an intuition like why lattices. Okay. So what the book does in section 6 is start with a very simple idea of a crypto system that is not secure, but like is going to get us on the way. Okay, so suppose you start with a large modulus Q, positive integer, and then you take two secret positive integers f and g, so that now we're going to start sizing things, which is an important thing in lattice cryptography. They are both like relatively small. For example, f is less than, say, the square root of q over 2, and g is also less than the square root of q over 2, but is at least square root of q over 4. Okay, and then I want f to be coprime with q. Sorry for the g and the q, sometimes they're a little bit similar. Okay, so I'm choosing f and g to be relatively small integers, and I want for sure f to be coprime with the modulus, which is q. And typically, what do I want a number to be coprime? Because I have to find the inverse, right? So then I will in fact compute the inverse of f times g, obviously mod q, and I will call this h. Okay, so now of course h will be between 0 and q. Cool. Now this is all relatively tame. So the point is that now f and g are small, and in fact they are both like order of square root of q essentially, and the quantity h on the other end is in general order of q. Yes? Which is much larger. So I'm going to store f and g as my private key, and I'm going to publish this as my public key. Right? Kind of makes sense. Now, how do I encrypt a message? So the entire point of this crypto system, which is what is going to lead into like lattice cryptography, is that size matters, if you want to say it in a funny way. And so our message is also going to be, so if I take a bunch of random small objects, then they're easier to identify. Okay? But I can hide them into big objects at a very, very high level. So yeah, so here's the next. So suppose that I want to encrypt. So this is like the key generation. Now how do I encrypt? I'm going to choose my message to be an integer, always positive, but like also small, say less than the square root of q over 4. And then, as it happened in some other crypto systems that we've seen, we have like a random component. Right? So we have an ephemeral key r that is also small. Okay, and now the ciphertext will be, I'm going to follow the notation here, E, which is RH plus M. Okay, mod Q. All right. So what I'm doing is, so in a very broad sense, we'll get back to this. This should kind of recall something that we've already seen already, right? And what is that exactly? I'm thinking suggestions.
It's a little bit like, what's the crypto scheme based on the Diffie-Hellman?
Oh, like El-Gamal?
Yeah, a little bit, but not exactly.
It does look like El-Gamal, but here it looks to me like, okay, maybe I'll give a hint. What happens, how do I, if I take a linear code, how do I encode and how do I encrypt the McAleese, right? If I have a matrix G, right, what I do is mg plus e, right? Right? Now you see this? So here, what we were doing in code-based crypto is I form a code word, and then I add an error vector, right, to distort it. And this is kind of similar, except it's in a different realm. So this is not a code word in a code. It's just like, if you imagine that h is your public value, like g was, right? It's kind of like in the realm of integers, this is like a big integer, and R and M are small integers. So it's kind of, you know, it really looks like the same when you look at it. It looks similar, right? But I'm not really creating a code word here. I'm just creating an integer and then adding another integer, and both these integers are small. They're small in the normal sense of like the absolute value, okay, or modulo anyway. Cool. So so this is kind of cool. And then there's another difference is that here our message goes in here, and then we add some noise. Whereas here we're kind of doing the opposite, because we put our message kind of like in the noise, and the randomness in here. Now there is no reason in principle, okay, why we can't do this with McAleese as well. So if you take McAleese, which encrypts like this, you can imagine that like you can take your message and put it in here, and you just generate M at random. Right? It's the same thing, because once you decode, you recover both M and E anyway. Right? So for practical reasons, McAleese did the obvious thing, which is you put your message into the bit string M, and then it's easy to generate E as a fixed weight vector, because it has to be low Hamming, so like just fixed number of positions. But in principle, you could do the opposite. So you can imagine that McAleese really carries, so you know, you can choose one to be the randomness and the other one to be the message, or vice versa. And here it's more convenient to do this instead. But it's kind of the same structure, kind of. I mean, at least you should see some similarity. Okay? Okay, good. So now the idea is that we get this ciphertext, and obviously we want to recover M. But okay, we can do it. And the technique, so when we did this with linear codes, then you know this is a code, so it's like a vector, right, that lives in a certain vector space, and then we have like the property of the code to use the decoding algorithm and get the error. Now we're living in integers, right? We're living in ZQ, basically, because Q is my modulus. So how do I remove the error from my ciphertext? Okay. The key point is that these quantities are small. All the quantities involved are small. Okay. So here's what I'm going to do in the decryption algorithm, which is the most interesting. First, I'm going to compute the value A, which is Fe, okay, mod Q. And then I will compute B, which is F inverse A. So you're like, okay, wait, what are you doing? You're multiplying by F, and then you multiply by F inverse. So this should cancel out. But in the process, what I'm going to do is I'm going to take this modulo G, right? And the modulo G means that the G part is going to go away. And so now let's see that this actually gives me M. Okay, let's verify that. If you take A, this is Fe, which is FRH plus FM, right? But what is H? Is F inverse G. So this is F inverse G plus FM, right? Now, obviously these are integers, so they commute, so I can just cancel this out, and I just get RG plus FM, okay? It's just simple algebra. All of this is modulo Q, yeah? Good, so now I have this quantity, and I multiply by F inverse. So I will get F inverse RG plus F inverse FM, right? Makes sense? Now, obviously, this goes away, and the key is I'm going to take this modulo G. So if I take this mod G, then this thing is 0, because there's a G there. And so I get exactly M. Okay?
Mod G.
Mod G, yes. And that's a very good point, Misha, because now the point is, how can I be sure that this is actually the M that I want? Because we haven't discussed sizes yet, but I told you that size is crucial, right? So if you look at this quantity here, what is Rg plus Fm? R is less than Q over 2 square root. G is also less than square root of Q over 2, okay? And then F and M, same thing. So in the end, this is less than square root of Q over 2 times square root of Q over 2 plus square root of Q over 2 times square root of Q over 4. Yeah?
Mm-hmm.
Now square root, it's the square, so it goes away. So you just get, in the end, that this is less than Q when you sum. Because this is Q over 2, and this is actually less than Q over 2. So in the end, if this was Q over 2 plus Q over 2, that would be exactly Q. But this is a Q over 4, so this is something smaller, and the sum then is definitely strictly smaller than Q. What does it mean that it's literally smaller than Q? Is that when you take modulo Q, this is actually the integer, it's not something bigger that you've reduced modulo Q. So you actually have no modulo reduction to do. And so because this is small, then you get an exact value, okay? And then again, when you do this, right, what happens is that B modulo G will be exact value because M is less than square root of Q over 4. Yes? And this is definitely less than G. So you have an equality of integers now, you're not doing congruences anymore. And so then you can be sure that when you do this, it's actually going to give you the correct message. Okay? It is in a distorted way, if you want, when you start, at least from my point of view, but also in a way, when you start from, say, like coding theory, for example, and you have like this error, it's easier to visualize that you have like a bit string and you just like distort some of the bits, and then you correct them. And here is a bit more obscure, but the idea is very, very similar, is that I distorted some quantity with this other quantity, but it's small. So because it's small, I can like undo it and recover exactly that quantity there, okay? There is a parallel with the fact that in coding theory, you can only recover the error if it's small, okay? And same thing here, it's all small integers, so when you fix the appropriate sizes, then you can get rid of it, okay? Except that in this case, M was actually my message and R was my randomness, but again, one could choose the other way around.
But you didn't recover R in this case.
In this case, you don't recover R, and this is why we put the message in the M. Okay.
Is there a way to recover R or no?
Well, I suppose you could, like, at some point, subtract M from there,
Oh.
and then take the inverse of H. So it could work as well, but you know, there would be more work in that case. So at the very least, you have to do like more operations, so it doesn't make sense to put the message in there. Okay, so
R gets to have a higher value.
huh?
R gets to have a higher
Yeah, but I mean, depending on how you choose Q and how you encode, it doesn't really matter. Okay, you probably want to save the computation time. Okay, so the idea is not as intuitive as the codes, but it's kind of following the same path. And now let's think for a moment about. So this is a very simple crypto system, just based on modular integers. Like, where are the lattices in this, right? So how can I actually attack the system? Well, of course, you could try a brute force search. So if you tried brute force, for example, over all the possible plain text or all the possible private keys, then this is obviously like an OQ sort of endeavor. Yeah, so that if Q is big enough, this is not feasible, of course. And you should always start from the basics, so let's make sure that at least Q is big enough that you cannot perform perform a brute search. But now, maybe let's look at the attacker task in a little bit more detail. So suppose that I'm trying even like the simplest attack, which is actually recovering the private key. Yes. So if I'm trying to recover the private key FG from the public key, which is Q and H. I mean, technically H is the public key, Q is the known modulus, like for RSA. Yes. So, but anyway, I want to recover this from the public information. So if I can find any pair of positive integers, they don't have to be exactly F and G. They could be, say, capital F and capital G, right? And then you have the FH is equal to G mod Q, right? That's exactly what this equation is. This one. But of course, I need to have both F and G each order square root of Q, otherwise they don't satisfy the size requirement, right? So this would be an alternative key. It may not be exactly the same key, but it would work for decryption. It could be another integer, what do you know, right? It could be another integer of that size that still verifies that equation. And so, yeah, so if you rewrite these congruents, it's actually, this is equivalent to FH equal to G plus a multiple of Q, right? Okay, so our task then is to find two integers that are relatively small with the property that essentially now we can think of these as vectors and we're getting closer to our goal. So I can also write this in this way. F times the vector 1H minus R times the vector 0Q is equal to FG. Okay? This makes sense. Because F minus 0 is equal to F, and FH minus RQ is equal to G. If you look component by component. Okay, so the first one is basic, the first one is like F equal F, the second one is FH minus RQ equal G. Okay, so we can think of this as being multiples to these two vectors that are known, right? H is known and Q is known. So in other words, I'm saying if I write V1 equal 1H and V2 equal 0Q, then what I'm really looking for is a linear combination, right? Let's call it W such that A1 V1 plus A2 V2 is equal to this vector, which is small. Okay? So W is small in the sense that it is O square root of Q. Okay? Well, not that's a vector now, so that means component by component. Okay? And of course, this A1 and A2 are integers. Okay? So it's not our typical linear combination, because when we think of linear combinations, the factors are anything. But here we're restricting to just integer multiples of two fixed vectors. Okay? So now what have I done? I've transformed the problem that comes from the crypto system into an equivalent problem, which is basically the problem of finding a small vector, right, among a linear combination of these. I can think of this as a basis now, right? If I think of this as a basis, then there would be a vector space. If you take a basis, what is a vector space? It consists of all the multiples and combinations of that basis, right? Except that these are integers. So it's not a full vector space, but it's only the integer combination of these bases. Well, guess what? This is exactly what a lattice is. Okay? So a lattice is essentially the space consisting of all the vectors of the form a1, v1 plus a2, v2, such that a1, a2 are in Z. So what is a lattice in other words? In this case, it's a two-dimensional lattice. It's exactly the set of integer linear combination of a specific basis. Two-dimensional means it's just two vectors. Okay? And now you can even see why this is called a lattice in a sense. And then we'll obviously see more of this. Why is it called a lattice? Suppose that this is one vector and this is the other vector. Yes, like a basis. So what is the lattice then? It's integer combinations. For example, you take 1 times this plus 0 times that, it gives you this one. If you take 1 times this plus this is v1, this is v2, yeah? But if you take v1 plus v2, oh, it's this vector here, right? Right, which you did like this one and this one. What is v1 plus 2v2? Oh, it's this one, right? What if it's v1 minus v2? Okay, so you see that you basically get like this, where all the points are a linear combination of your elements in the basis. But what is the lattice though? It's not the whole thing, it's just these points here, because I'm taking only integers, right? So exactly like a lattice, you know what a lattice is in English, is like a net, right? And then the lattice itself is just the dots. And imagine that the crosses connecting the dots is just the linear combination of the vectors in the basis. Okay? Does it make sense? This is an important concept. So it's called a lattice because in 2 dimensions it looks like this. Now you can imagine, what if I take, for example, 3 vectors? Then it's a 3-dimensional lattice. It's like these points in the space. And vice versa. So you can now do it with large dimension. And it's the same thing. You can easily imagine this generalizes, right? But now my crypto system is based on the hardness of finding a small vector in lattice. Why? Because if I can't find the small vectors in lattice, then I have this security reduction. Okay? Remember, we've done more than one security reduction earlier in the course. So essentially, if I can't do that, well then yes, given this pair of values here, then I can basically set up a lattice with these vectors. I apply my fast algorithm for solving that. It will return me a small vector, and that is going to work for my purposes. It may not be exactly the original private key, but it will still work. Okay? So then this now ties this apparently innocent crypto system with the idea of lattices. Okay? And unfortunately, of course, this particular system is not secure because already Gauss, which every mathematician should know, already had an algorithm for finding such vectors in 2 dimensions. Okay, and so this can be used straight away to solve this crypto system. But the underlying idea is still valid, right? Because now you're like, okay, in 2 dimensions I can easily find like even this base, what is a short vector, what is a small vector. And remember, the key idea is what is small in this case, right? Because the structure of the crypto system kind of reminds me of what we were doing with linear codes, but my notion of smallness is not in the Hamming sense, where I have vectors and I look at few positions, but it's rather in this what is called in the Euclidean sense. It's the magnitude of the positions. Because now I'm looking at these vectors here, where all the elements are component by component less than, for example, the square root of q over 4 or something. So I'm looking at small components. So if q is like 100, then I want like my components to be like between 3 and minus 3. Okay, something like this. And then of course when you scale up in proportion. Okay? Good. So this is the idea of a very simple crypto system that already like brings us to lattices. Any questions on this? We good? Okay, so now let's take one more step forward, and let's talk about knapsacks a little bit. Okay, so what is a knapsack, and how do we use this? Okay, so basically, the classical knapsack problem is finding a combination of numbers that work towards some goal. And in a more general form, you can formulate it this way. This is known as subset sum problem. And it's very intuitive. So see, if you have a list of integers, for example, m1, m2, mn, and you have an integer s, right? Find a subset that sums to s. Okay? It's something very intuitive. And in this case, I may do an exception to show you a practical example. Suppose that you have the list M to be 2, 3, 4, 9, 14, 23, right? And I give you S equal 27. Can you find a subset of the elements that sums to 27?
Yes, 23 and 4.
23 and 4, but also you have 4, 9, and 14. Yes? Easy. So then, there's more than one solution, obviously, and so then you can ask, okay, is my solution smaller than a certain threshold? Okay, and this is relatively easy if you have this kind of sequence and these kind of numbers. But of course, if the sequence gets bigger and then you change stuff, this problem gets harder and harder. Okay, so how can we, so you also said like there's 4 and 23, okay, and so on. On the other hand, there could be integers that don't have a solution as well. Okay? So it depends, and so we have to define it a little bit more carefully. So in other words, I'm looking for S to be a solution of this equation here, I going from 1 to n, where the vector x1, xn is binary. Right? Because I'm not taking multiples, but I'm taking just like either I take the number or I don't take the number. Okay, so I'm looking for a binary string. And of course, one thing you can do to solve this problem is check all the possible strings. Well, there's 2 to the n of them. This is not very practical, right? Because as soon as n is big enough, even if n is like 80, which is not very big at all, then you probably won't do it. But of course, we have seen before that we have collision algorithms, and then we can make 2 lists, for example, right? We can make a list A and a list B, and in A we put the first half, and in B we put the second half, right? And then what we can do is that we can say, call AI the sum of the MI. So let's take a particular combination in the first half, and then let's see what Bj is as S minus that. Right, and see if we find a match. Because if we find a match, then this is equal to that, and then the sum is S. Right? Obviously, like if this is equal to that, then you take it on the other side. Okay. So, so if you can do this, so you're trying to find a match between this list and this list. We do all the list, all the values AI, and all the values Bj. Now there's only n half of those. And so with a collision algorithm, you only really have like 2 to the n over 2, let's say, order off. Okay? Because there's some time to put the solutions together.
You also have the additional space complexity.
Yes, of course. I mean, there was a concern as well with like discrete logarithm stuff and things. But basically, we have 2 to the n over 2 plus some time for comparing and matching and putting together things. Okay. So now, in general, it's difficult to solve a random instance of this problem. Now though, if you add some trapdoor information, this could become easy, and this is exactly what we're gonna do. Okay, so first of all, we have to define a couple more things. We talk about a super increasing sequence. If I have the list, if I have a list of integers such that the next one is at least as big as twice the previous one. Okay, so these are my R1, Rn. Okay, so I can say obviously that my sequence is increasing. I don't have to define this. If every element is bigger or equal than the previous one, like this one. But super increasing means that there is a gap. So not only each element is bigger than the previous one, it's actually much bigger than the previous one. Right? And so why is that called? Well, what we can say is that it's easy to see that if a sequence is super increasing, then in fact, for every k less than n, or actually less or equal n, we have that rk is not only bigger than rk minus 1, but it's also bigger than rk minus 1 plus rk minus 2 plus r1. So not only every integer is bigger than the previous one, but it's bigger than twice the previous one, and obviously the previous one was bigger than twice the previous one, and so on. So by induction, you can even see that every integer is now bigger than the entire sum of the previous ones. Okay, so now of course, this makes it easier to solve a knapsack problem, because you can say like, oh, if this integer is in there, then it contains the entire sum, and then should I choose it or should I move on? Okay. So basically, what you can do is you can just loop. So you can just loop, right, from m down to 1, right? And say like, okay, take my integer. Is it bigger than half this? Then I take the integer, or is it not? Right. So what you can do is, if s is greater than mi, then I take that, right, and then subtract, and then set. You can say set s equal to s minus mi, and otherwise set xi equals 0. Okay, because I know that if it's bigger, then it must contain all the previous ones. Otherwise, it doesn't. Okay, so this is easy if we have a super increasing sequence.
Can we do a similar reduction for block super increasing sequences?
Huh?
If the sequence increases by blocks in the same pattern, probably do the same.
Yeah, this is an interesting question. So I just want to show you an example of this because it may help understanding what's going on. Right? So let's set m to be 3, 11, 24, 50, and 150. You can see that this is super increasing according to our definition, because every element is bigger than double the previous one. Okay. So now if I ask you s equal 142, you're gonna say, okay, let's start from the end, right? Is s bigger than 115? Yes. Right? S is bigger than 115, so I'm gonna take 1 here, right? Because certainly has to contain 115, otherwise there's just not enough numbers to reach 142. Okay? Because the rest are smaller than the sum of it. So that's what's okay. So now I'm gonna take this, and then I'm gonna bring s down to 142 minus 115.
27.
Which is 27, correct? And now I'm going to compare, okay, is this bigger than the next one? No. So I'm going to take a 0 here. Okay? But it is bigger than 24, so I'm going to take a 1 here. Right? And so then I bring this down to 27 minus 24, which is 3. And obviously at this point I'm done, right? Because you know that this is exactly that. So that was my sequence. And 142 is 3 plus 24 plus 150. and my solution was x, the vector 1, 0, 1, 0. Okay? So if I have a super increasing sequence, then this is like relatively easy. Okay, so now let's see at how we can do this, how we can use this in cryptography. So there's a crypto system by Merkle and Hellman, and this is the same Hellman that did Diffie-Hellman stuff. So we're playing around with integers. So suppose you start with a private. So here is the key generation. You start with a private R1 Rn, which is super increasing sequence. And then now you want basically choosing two integers a and b so that b is actually bigger than twice the last element, and you want a and b to be coprimed. And now you create a new sequence that is not going to be super increasing, because now you know that if the sequence is not super increasing, then the problem is hard, or at least intuitively, right? So you're going to create a new sequence M, which is A Ri mod B. Okay? So you're scaling everything by A, but whenever it goes beyond the threshold, you're just going to reduce mod B. So then every Mi is less than B, of course, right? Because we said that B was twice Rn, so it's at least twice as big as the biggest one. So you know that everything is less than B. Now this is going to be your public key. This is going to be a sequence, but not a super increasing one anymore. Why? Because you take reduction modulo B, right? So now that this sequence looks like completely random, or at least like not super increasing anymore. Okay, so that's good, because that means, what am I going to do to encrypt? So to encrypt, I'm going to move here. Now I have a sequence M, which is my public key, and I'll take my message and I'll put it in a vector X, which is exactly the combination of the elements, right? So this is like x1, xn, right? Binary vector. And so I'll form S to be x times m. Okay. And so this is exactly sum of xi and I. Yes. Okay, so this is very easy. And how do I decrypt? Well, this is the interesting part as usual, right? So what I'm going to do is, I don't know how to decrypt if I have a non-super increasing sequence, but if I have a super increasing one, then it's easy, right? So what I'm going to do is take S and create S prime, which is A inverse S. And again, this is mod B. And then you can now solve the subset time problem, because this is now going to be a super increasing sequence. And let's see that this is true. What is S equal A inverse S? This is going to be equal to A inverse times this sum, right? Which is in fact A inverse times the sum of xi A Ri, right? Because Mi was A Ri. Every element is multiplied by A, so I can take this as a common factor, right? So I can take this out, and then cancels out with that. So this is in fact exactly the sum of xi Ri. And now this sum of xi Ri is a subset sum problem in the sequence Ri that is super increasing. So I can now apply my solver and find the xi's, which is exactly my message. Cool. So now, of course, we haven't talked about sizes, but the important part is that because B is greater than 2Rn, right, we know that the sum of xi Ri is certainly less than the sum of all the Ri's, which would be all the xi's being 1.
Which is less than
First random mode. And then obviously this is less than 2Rn because the sequence is super increasing. And then of course this is less than B. So when I do this, I'm going to find the exact one that I want. Okay. So if I choose S prime modulo B, right, then I get an equality rather than just a congruence. Okay.
And the solver, it's unique when it's super increasing, right?
Yes.
Like we went over that.
Yes. Yes.
But it's not necessarily unique when it's not.
Exactly. And so now you're facing. So if you're just seeing the S and the M, you have no idea, or you should have no idea what the S is. Okay. So here's the example from before. At this point, we can continue it. It was 3, 11, 24, 50, and 150. Okay. We have seen that it's easy to recognize a number in this. Right. We did it like really quickly. But now I'm going to choose A to be my offset factor, and B, I want it to be at least twice as much as that. So I'll take, say, 250, right? And so then I multiply my whole sequence by 115 and reduce modulo 250. So that gets me M, which is this, times 113, modulo 250, 89, right? 243, 212, 150, 245. Okay, it's not even increasing anymore. It's completely. I mean, you know that when you multiply and then reduce, it behaves like that, right? So now you get this sequence, and yes, the book says not even close to being super increasing. So now, of course, one thing you could do that the book is like nonchalantly like, what you do is you just permute. If you permute the sequence, and that was super increasing, then what you could find would be a solution in permuted order, then you just unpermute it, right? But this is not even the case. So it's important that it's not the order, but it's important that it's actually the values are not super increasing. Okay, now suppose that I'm sending X to be exactly 10101. That's my message, right? I encode it in a bit string, it's a very natural thing. So I'll just do this times that. It means that it's 89 plus 212 plus 245, right? Which gives me my ciphertext as this. Okay. Now, of course, I want this modulo B. So it's just 46. Actually, wait. I do this in decryption, so I don't want to do things wrong. So I now do this. This is my ciphertext. This doesn't have to be reduced to modulo B. I will reduce once I use the private key, which is A. Also because A and B are secret, of course. Okay, so now this is my ciphertext. How do I decrypt this? In principle, given 546 in this sequence, it's not easy to see which one's the combination that gives me that. In principle, at least. Of course, this is a toy example, yes? So upon receiving this S, I'm going to compute S prime, which is the inverse of A times S mod B. So it's going to be 177 times 546 mod 250, and you get 142. Well now 142, I can solve it in a super increasing sequence. This one, the original one, right? And in fact, we did that in the example before. It gives me exactly that. I don't have to do the calculations again, right? You see, 142 is bigger than 115, blah, blah, blah. So that gives me exactly this sequence here. Okay, and then I know because of these restrictions on the size that that's exactly the message I was looking for. Okay. So these kind of crypto systems are like of knapsack type. And of course, again, this is a very simple one, but the basic idea is valid. And in fact, when you think about it, wait, let's look at this again. You are taking a bunch of elements and a combination of them which is binary. Yes? I'm doing this with integers. Okay, so now what is these elements instead of being integers are vectors. Okay, so I have like a vector v1, a vector v2, a vector v3, right? And then I take a linear combination of some of these and so on, right? It's still a knapsack problem, except instead of having integers, I have vectors, right? Make sense? Okay, one thing like this we have already seen. Look at this. If I take a matrix H, okay, let's say the H is in, say, even F2 R times N. Okay, so this is like big matrix R by N, right? And I'm looking now at columns like this. Each of these columns is going to be a certain column HI. Yes? Okay, then any combination of these columns will give me a different vector, right? So what if I take a binary combination of this, like a sum of the HI times, I'm going to call it EI to give you a hint. And this goes from 1 to n. But then this is equivalent as multiplying this times the vector E1, E2, En. Right? Yes? Because E1 multiplies the first column, E2 multiplies the second column, and En multiplies the last column, right? These are all 0, 1s. So you either select the column or don't select the column, right? And everything works like modulo 2, right? Then how can I write this? Well, this is exactly H times E transpose, where E is this vector here, equal S. Now, if you remember, like 2 lectures ago, we already saw this. What is this? It's exactly the syndrome of the vector E. Right? And now, if I think in coding theory, with my coding theory hat, well, the syndrome of the vector E, if this is 0, then E is a code word, right? But if this is not 0, if this is actually a proper value, then E is like a vector, is like an error vector, right? And then this is a knapsack type crypto system of a particular kind, because E, I know, has like a certain weight. So like only few of these EIs are actually 1s, the rest are 0s. And I know how to find a solution, right? If I have few components here. This is exactly the syndrome, the coding problem. And I know that the solution exists and is unique as long as the weight in terms of Hamming of this vector here is low. So this is what crypto system is exactly with the writer crypto system, right? Which we saw was equivalent to Michaelis. But if you think about it, what is the writer crypto system exactly? Is a knapsack on the columns of the matrix H. And now, of course, we're changing the rules of the game. Now we're not using integers and super increasing sequences. We're using binary vectors. And it doesn't matter that my sequence is super increasing, but it depends on the weight, the solution having a low weight. So it's kind of like a modified knapsack type system, right? But it's the same nature. I'm looking basically for a specific combination of columns that gives me that vector S. Aha. So this is kind of cool because I think like it connects areas that at the beginning looked very, very different, very remote from each other. Okay? And we already saw that the previous crypto system kind of looks like Michaelis. Now this new crypto system kind of looks like Niederreiter. So it really, this parallel keeps going on. Okay? So if we take, instead of summing super increasing sequence of integers, we sum binary vectors of a matrix, then of course my method for decrypting is going to be different, right? For super increasing sequence of integers, my decoding algorithm is use the simple like loop thingy that we described before, where you just compare with half. Okay, that's actually not a very sophisticated algorithm, right? In the case of this particular knapsack, it depends how H is formed, and then I run the decoding algorithm of the code associated with it that you can see escalates, but the idea, the underlying idea is the same. I have a knapsack that I know how to solve because the H I can modify. I remember what I do when I presented with my ciphertext in Niederreiter. I unscramble it, right? I have a ciphertext S, which is H times E, what I do is I multiply this by S inverse, right? So that I get S inverse H times E. Now this thing is some sort of linear code that I know how to decode, right? And that's kind of the same as what I do here, right? Same idea. So I transform, for example, look at the parallel, a sequence which is like random looking to a super increasing sequence, and I know how to recover that. Same thing here, I transform a random looking matrix into a matrix that is recognizable parity check for a code, and then I know how to decode that. Okay? Same idea. And in fact, what this is leading towards is the following. Now, if I take these vectors to be, for example, binary vectors and put them in this column like this, then this looks like a parity check matrix for a linear code. But in fact, I can think of these in another way. So, for example, I can also say if I build a matrix in this way, 2 and then all zeros, and then 1 in the end, and then 0, 2, 0, and then 1 in the end, and then 0, 0, 2, and then 1 in the end, all the way down to 0, 0, 0, 2, 1. And then here I'm going to put M1, M2, Mn, S. Right? Then I can call this vector V1, this vector V2, this vector Vn, and the last one say Vn plus 1. So I take the rows of this matrix, and then this corresponds to writing a subset sum from the sequence M1, Mn, right? Because then you can see that each vector here is going to be a combination. So if you take integer combinations of V1, Vn plus 1, and you take linear combination of this, is going to tell you so if x, x1, xn is a solution, then T, I write T as a sum from xi vi minus Vn plus 1. And this is going to be something like 2x1 minus 1, 2x2 minus 1, and then 0 in the end. Because S is x1 m1 plus xn mn. Okay, so I can formulate a subset sum of this form by putting down a matrix like this, where I have my elements here and the target, and then because the sequence is super increasing, I just have this bunch of 2's, and then this selects the ones that I am selecting. So now this becomes a lattice problem again, okay? Because all the xi's are either 0 or 1, right? And so the vector itself, so if I look for this vector t, this is quite short in terms of coordinates, okay? So let's say that t, it's about square root of n, for example. But the super increasing sequence is composed of bigger integers, right? And we should elaborate on this a little bit more, because this is going to be an important part. So let's think about this. If I have the vector x1, xn, and this is in 0, 1 to the n, we already saw that we have 2 to the n of those, right? And with a collision algorithm, we can actually simplify this, the attack time to 2 to the n over 2. So how should we choose the values of the other parameters? Because in the simple crypto system that we saw before, remember we took like q over 2 square root and stuff. Okay, so let's start from for example, R1, first element in my sequence. How big should this be? Well, if this is too small, then there are some easy attacks. So actually, this one should be already bigger than 2 to the n. And then because, of course, Rn is bigger than 2 Rn minus 1, which is bigger than 2 Rn minus 2, and so on, this is in particular bigger than 4 Rn minus 2, right? I should say 4 Rn minus 2, and this is bigger than 8 Rn minus 3, and so on. Because every time I'm multiplying by 2, and then this is bigger, obviously, than 2 to the n R1, which is bigger than 2 to 2n, because this is also bigger than 2 to the n. So then B, which is bigger than 2Rn, should be exactly 2 to the 2n plus 1, or at least in this problem here. Okay, and so essentially, my public key Mi will also be order of 2 to the 2n, and same for S, because it's just a sum of integers in that order. Cool. So 2n plus 1 or 2n is the same thing. Okay, so my MIs are 2 to the 2n. So if I want to have, for example, 128 bits of security, then I have to take my MIs to be order of 2 to the 256. And then so for these. Okay, so you basically want, so for example, for 128, you want like 256 bit numbers. This is still smaller than RSA, yes? Okay, so, but however, the public key size is n integers, because you have like n of these. Whereas for RSA you have just one modulus. So for RSA you have like one modulus, which is 1024 bits. Yes. And here you have a bunch of 256, say, bit integers, but you have n of them. So in fact, your public key size is like 2n squared, right? Because it's 2n bits times n. Okay, the example you have on the book is for n equal 160, and that already gets you this many bits, right, which you compare with RSA, it's much bigger. Okay, but anyway, this is looking like a disadvantage, but of course, in terms of speed, the algorithm is much faster. Because we've seen that, I mean, first of all, summing the integers is basically free, because it's just binary combination, so you're really just summing integers. And then even the decoding part, which is like the fast looping algorithm, is just comparisons, and you just put 1 or 0, right? So that's elementary. So even compared to RSA, which you're doing like exponentiations and multiplications modulo, and you know this is going to be much faster, but you pay some price in size.
Your message size is only 160 bits.
Yeah, of course, the message size is very small. Yes, too. So, but I mean, the ciphertext is yes, it's just one element. So it's characterized by having like quite short messages.
So the ciphertext expansion is not that bad
The
though.
ciphertext expansion, the message expansion is like 2 to 1. So it's not that bad.
It's not bad.
Yeah, correct. All right, so because it's 2n bits. Yeah, your initial message was n. So yeah, it's not bad at all. So, but this is again, this is like a very intuitive. This is not the actual crypto system we're interested in, but it's just a leading into, because before we said, okay, now we have the vector here that is something like square root of n, but my sequence is really big. It's like 2 to the 2n. And so basically we can assume that this vector here, which is a vector in this lattice, is the shortest vector in the lattice. Okay? Because all the other ones are probably going to have like really big components, right?
Shortest is in norm, small.
Shortest is in norm, exactly, yes, as in norm. Okay? And so basically, before we said, if we have an algorithm to find a short vector, in the previous intuitive crypto system, we can solve it. Same here, if we're able to find this vector, then that basically is giving us a solution to this problem. And so it turns out that the hard problem here is finding the short vectors in a lattice, which is the equivalent in this new metric of finding, like, for example, low weight vector in a code, right? And so you see why the two areas are similar, and I think it's usually more intuitive to do the coding theory ones first, but it's a similar type of problem that is hard. And yes, so it boils down to this like short vector problem in the lattice. Of course, the key point is you have a certain crypto system. So now you can imagine the crypto system is going to be described in a certain way. It doesn't have to be the congruence one, or it doesn't have to be the knapsack one. But basically, it boils down to building a certain lattice of a certain type, and then looking for short vectors in that lattice. So what changes is the lattice you're considering. And so depending on how good your better choice is, then you have good or bad luck. So we can conclude today with like just a few definitions about lattices. Okay, and then we will see actual example of crypto systems next time. Make sense? So what is a lattice then? We can make a formal definition. Let's take vectors v1, vn in R to the n, to the m. Let's have these linearly independent vectors. Okay, so these are length m vectors, and I take n of them. Okay. Then you see that the lattice L generated by v1, vn is exactly the set L equal to a1, v1 plus an, vn, so that these are integers. We already saw this in 2 dimensions. Okay, now I can say it's in n dimensions. Each of these is a vector of length n. Okay. All right. So a basis is any set of linearly independent vectors, of course. And the dimension is the number of vectors in a basis. In this case, n. Okay, so now so what we can do is, if I have a basis v1, vn, and then I have another basis w1, wn, right? Suppose I have 2 different bases. Then what I can do is I can always write like w1 as a combination v1 plus a1n vn, right? And then also w2 will be a certain combination a21 v1 plus a2n vn, right? And similarly, like wn would be also an a n1 v1 plus a_n vn. Right, so if I have 2 bases, I can always express one in terms of the other one, and they are related by these coefficients a1, an, so on. So this is like if I just take the matrix of coefficients a, which is made of like the aij's, right? Now the interesting thing is like these are all they're all integer combinations. Okay. And so what is the point? If I consider A inverse now, A inverse is the matrix that brings the V's into the W's, the other way around. because I can express the W's in terms of V with the matrix A, or I can express the V's in terms of W's with the matrix A inverse. Make sense? So now, of course, this has to be invertible. What does it mean that invertible? The determinant is not zero. And the thing is that, in fact, we have that the determinant of AA inverse, right? On one hand, this is pure matrix theory. Right? On one hand, AA inverse is the identity matrix, well, that has determinant 1, right? But on the other hand, this is equal to that A times that A inverse. And these have to be integers. So what are the only integers that work? Plus and minus 1. Okay? And so A inverse does have integer entries. And so any two bases of lattices are related by a matrix A which has integer coefficients and determinant equal to plus or minus 1. So we can easily switch between bases of lattices. Okay? Okay? Is that making sense? So then we talk about a specific type of lattices. We say that a lattice is integral or integer, right? If all vectors have integer coordinates. Okay, so now we restrict to z to the m rather than r to the m. Okay, this is going to be more convenient. And so here we have a small numerical example. Suppose that I take now a small dimension 3 lattice, say for example, like I take V1 to be 2, 1, 3, V2 to be 1, 2, 0, and V3 to be 2, minus 3, minus 5. And so, okay, now I can form a matrix using these as rows. So I'll just take A to be 2, 1, 3, 1, 2, 0, 2, minus 3, minus 5, right? And we can generate 3 new vectors, for example, W1 equal to V1 plus V3, W2 equal to V1 minus V2 plus 2V3, and W3 V2 plus 2V3. Sorry, V1 plus 2V2, I think. Okay, there's an error in the book. So then basically what we'll do is we multiply this matrix A by the matrix U, which is given by these coefficients, which is going to be 1, 1, 1, because V1 is always present, and then 0, negative 1, 2, and then 0, 2, 0. Sorry, 1, 2, 0, because V3 is here. Okay? And so now we find that B equal to UA, whatever matrix you get by multiplying this with this, has, so now this matrix here has determinant 1, actually negative 1, sorry. So the vectors W1, W2, W3 are also a basis for the lattice. Okay? So before we didn't know if these W1, W2, W3 are linearly independent, but we know because they are related by this change of basis, which is determinant negative 1. Okay? You can also write U inverse, which is the change of basis in the other direction, and it will give you V1, V2, V3 as function of W1, W2, W3. Okay, so there is this important idea of bases in the lattice. Okay, so we can always change bases in the lattice if we take basically the change of basis U as part of GL of Z of dimension n. This is the general linear group, right? The group of invertible matrices. Okay. And so now, to conclude, the next time this is what we will start from. let's look at subgroups. So if you take a subset L of R to the m, we say that this is an additive subgroup. If it's closed under addition and subtraction, of course. Right? But also this is a discrete additive subgroup, right? If there exists a constant epsilon with the following property, for every vector in L, we have the L intersected with the set of vectors W in R to the m, such that the norm of their difference is less than epsilon is just B itself. Okay? So in other words, basically, if you take a vector V in L and you draw a sphere around it of radius epsilon, then there is nothing else inside that ball. And again, we've kind of seen this idea for codes, where we have the code words and you have like a ball around it. But here now we're talking about Euclidean norm. Okay? Not about ones and zeros, because what you do in code words, you take these code words and then like they're like say binary vectors or QR vectors, doesn't matter, then you start changing coordinates one at a time and then you move away from the code words, right? Here is not about the changing the positions, but changing the values. So it's really, more and more making the idea that this is kind of like a different setting for a similar idea. I have a discrete object. This is going to be a discrete. So what is a lattice then? Is exactly a discrete RTD subgroup of this vector space here. Okay? And what is a code is exactly that is kind of like a sub vector space of a larger vector space or a finite field. Here we're not doing finite fields though, right? So it's different. So we have a new metric and things work in a similar but different way. And then what is interesting to see is that cryptography works in a similar but different way. So some things work better with code, some things work better with lattices, okay, and so on. We already have a picture essentially of the lattice with the points, but we can nail a couple more things down. Just to conclude, in 2 dimensions, we've seen that we can represent the lattice using like these bases, for example, and then I get like all these points here. That's my lattice, right? Now, if I have a basis, what is called a fundamental domain, right, is exactly this area here, which kind of gives the imprinting of the lattice, right? So it makes sense to define that mathematically and call it f of v1 vn. In this case, we have just 2 vectors, right? In the general case, we have n vectors, and we call this fundamental domain also fundamental parallelepiped, because in n dimensions, this is not just a 2-dimensional object that is parallelepiped, or n-dimensional parallelepiped. And so this is the set exactly of T1, V1, Tn, Vn, so that the Ti's are all between 0 and 1. Okay? It's that region contained within the basis. Okay? Another interesting part is that how do we use this fundamental domain? If I have a lattice L, okay, and then let F be a fundamental domain for L, then every vector W in Rn can be written as T plus V, these are vectors, right, for unique T is going to be a vector in my fundamental domain, and V is going to be a vector in the lattice. Okay, so you can think of T as being like the error that shifts. So you take a lattice and you shift it by a quantity that is always at most like something in the fundamental domain. Okay, so equivalently, if you take the union of the translated fundamental domain, so if you do something like F plus V in the translated fundamental domain by V, so this is all the vectors of the form T plus V, where T is in the fundamental domain, right? This covers Rn and the varying of V. Okay. Again, this is kind of what we do with the code words, and then like we shift them all with the cosets, and we cover the entire FQTN space. Okay. So that's good because this is kind of like leading us towards what we're going to do is that now we're going to take a vector, right, in the space. If I take a random vector in the space, it means I can always express it as a vector in the lattice plus a vector in the fundamental domain, which is kind of going to be in here, right? A vector in the fundamental domain will be like in the middle, right? Unless it's an extreme case. So that's not in the lattice. It's not in the lattice, but it's in the middle. But it's something, what is the fundamental domain? It's something small. So I'm setting myself up for, again, kind of what we did for the coding theory scenario where we had a code word and we shifted, right, by few positions, by a small error vector. Same thing here. Now if I take a vector in the lattice, I'm going to shift it by a vector in the fundamental domain, so something that is of small norm. And then, of course, as you can imagine now, the next step, which is what we're going to explore next, is if I do this in a clever way, if I'm able to recognize the fundamental domain, then I can cancel out this error, essentially. So if I have a good basis, then I can have a trapdoor for the cryptography. If I have a bad basis, then I'm not able to recognize what this fundamental domain shift is. And that's exactly how the lattice-based cryptography works. And the basic idea is the same as coding theory one. You intentionally distort your object with something that you can remove, but the public cannot. And in the case of coding theory, you have, for example, a parity check matrix that leads you to the coding algorithm, and then you scramble it to hide this. And here, what you're going to have is you're going to have a lattice, and you have a good basis for a lattice, and you're going to scramble it or hide it anyway, so that the public is given a bad basis for lattice, and then with that bad basis, you cannot do this. Okay, so this is a very important idea. And next lecture, we will exactly put this into action in a crypto system, right? So we'll finish nailing down a few more concepts, and then we'll see what kind of crypto systems we can do with this. Okay, but it's a very cool idea, and in a sense, they are both like two aspects of the same coin, and it's interesting to see that basically these are the two strongest ways of doing what we call now post-quantum cryptography, and they both revolve around the same idea of rather than trying some classical number theory problems, we have this idea of noisy elements in a certain space, and this seems to be really successful. Okay, excellent.